Good morning, everyone. My name is Amina Tabi, and I'm so excited to present my research on localization in wireless sensor networks using bio-inspired techniques. In this presentation, I will walk you through the background, the challenges, and the innovative solution in this field. So let's start with some background. Wireless sensor network consists of small distributed sensor nodes randomly or manually that are used to collect and transmit data wirelessly. These sensors are typically small with limited battery power and also limited computation and communication resources. In real-world application, wireless sensor networks are used in different scenarios like healthcare, military surveillance, environmental monitoring, etc. Now, let me introduce you the concept of localization in wireless sensor networks. But before that, let's consider this real-world example, a forest fire monitoring system, to make the concept more clearly and relatable. Here, sensors are deployed across large areas to detect fire events. Once a node has detected that the temperature is higher than a certain threshold, it sends a message to the base station. The message needs to indicate the location of node that detects the event. If we don't know the location of that node, the information of fire event will be meaningless. So simply, localization is the process of determining the position of sensor node within the networks. And like previous example, we can understand that quickly determining the precise location of the sensor detecting the incident is crucial for prompt and effective response. And so, localization is crucial for guaranteeing the efficiency of wireless sensor networks operations. One common solution to this problem is to use GPS, which is well known and widely used for localization. GPS can provide very accurate location data for each node. However, there are several reasons why GPS isn't always practical for wireless sensor network, such as cost, power consumption, and also GPS can't work very well in indoor situations. Because of that, a more practical approach is to equip only a few nodes called anchor node or beacon nodes with the GPS. So these sensors are used by localization techniques to estimate the location of the other sensors that we don't know their position, called unknown node or target node. Now we have two different sensors. The beacon sensor, the sensor that we do know their position using GPS, and the target sensors that the node that we don't know their position, and we use localization techniques to estimate their position. Localization techniques can be categorized into range-based and range-free. Range-based, like time of arrival or angle of arrival, use a precise distance or angle measurement. These methods are highly accurate, but often require more resources and are expensive due to the need for specialized hardware. On the other side, range-free like GV Help and Centroid don't rely to precise measurement and instead use connectivity information between nodes, making them less expensive but also less accurate. The localization process in wireless sensor network typically happens in two main phases. The ranging phase, the first phase, where the distance between nodes are measured. Then, in the estimation phase, these distance measurements are used to collect the positions of the target node. However, the real-world challenges like noise, obstacle, and interference can cause inaccuracies in the measurement obtained from the first phase or ranging phase. Therefore, the position obtained in the second phase are often inaccurate, and this leads to localization errors, which can impact the performance of the entire network. That's why the optimization is necessary. The goal is to minimize these errors, improving the accuracy of the positions, while also ensuring that the network's resources like energy and time are used efficiently. Now that we have discussed the importance of optimization in minimizing localization errors, let's look at one of the most effective ways to achieve this bio-inspired algorithm. These algorithms are inspired by natural behaviors such as the way animals forage for food, hunting packs, or move in swarm. By mimicking this process, the bio-inspired provide fast conversion rate and higher accuracy, making them effective in addressing the complex optimization problem. One of their key strengths is their ability to balance exploration, searching for optimal solution, and exploitation, enhancing those solutions. This makes them highly efficient at reducing localization error by finding the optimal coordinate for each NN node. Some example of bio-inspired algorithms include PSO or particle swarm optimization, which simulates bird flocking behavior to find optimal node position. Firefly algorithm, where firefly were attracted to buyer wants representing a better solution, and stop swarm algorithm inspired by the movement of stops to optimize the objective function. This flowchart illustrates the general workflow of localization process using bio-inspired algorithm. After deploying the sensor in the area, the distance between target and anchor node is measured. If the target node has anchors more or equal to 3 within its transmission range, this target node will know as a localizable node, and it will localize it using bio-inspired optimization algorithm. Now, for each target node, the bio-inspired algorithm is executed independent. Here, the process of bio-inspired algorithm initialize the parameter of bio-inspired algorithm. This algorithm will minimize the objective function, which represents the distance between estimated and calculated distance, to find the best position, update the best position, check the termination iteration. It's now we're gonna repeat the process. Obtain the optimal target node if the termination iteration is done, and check all the target node get localized. It's yes, it's the end of all the process of localization. It's now we're gonna repeat and check if there is any other localizable node. Many researchers have applied a bio-inspired algorithm to localization in wide sensor network. For example, DV help combining with with a fruit fly optimization algorithm. This combination reduces localization error significantly compared to the traditional DV-hop method. The second paper used Firefly algorithm to improve both accuracy and computation time or speed for node localization, achieving a localization error of just 1.004 meters with a very fast convergence time. In the third paper were introduced the SOPUS1, which outperformed other optimization algorithms like PSO and chicken swarm optimization. The third paper, where the author used the parallel Firefly algorithm. This version of Firefly algorithm divided fireflies into subgroups, which with each evolving independently after a set number of iterations. Subgroup exchange their better solution with neighboring groups to improve the results. Another work where the author trying to optimize the commonly technique, which is the centroid localization algorithm using artificial bee colony. The results show that the artificial bee colony have lower localization error compared to the basic centroid localization algorithm. Another work represents a new hybrid model called HBW and HBO, which is this model is introduced to tackle node localization issue in wireless sensor network by combining the block reader optimization and the honey badger algorithm. In this model, the selection between these two bio-inspired algorithms are based on the parameter M. Its performance is validation through comparison with traditional models, and simulation results indicate that this model or this hybrid model effectively minimizes errors and optimized node position in wireless sensor networks. In summary, localization is a critical challenge in wireless sensor network, and bio-inspired algorithms offer promising solutions. Each algorithm has its strengths and weaknesses, selecting the right one depending on the specific requirements of the network, such as accuracy, speed, or even energy. Thank you for your attention. I would be happy to take any question you may have.